So this video on exact sequence. So this is the lecture 13. We discussed in this video. We discussed exact sequence of module and dual module. So what is exact sequence? Exact sequence of module, or maybe vector space, or maybe a group also. It can be any other objects. So mi are R modules, and fi from mi to mi plus 1 are R homomorphisms. So f0 is from that f0 is from m0 to m1. So then f1 is from m1 to m2. So this is R homomorphism. This is m0 to m0 from m1. It is f0, then m1, f1, then up to say fn, mn to mm plus 1. It is called an exact sequence if the image of fi is kernel of fi plus 1. So this is the idea. So image of f0 must be equal to the kernel of fi plus 1, f1. That means what happened? That means if you take f1 compose f0, that is actually 0. So if you something is image in say f0 x in image, so this is in kernel. So f1 of f0 fx is 0. So that means fi plus 1 compose fi is actually the 0, the null homomorphism. Now, if it is a 3 module and start with a 0 module and end with a 0 module, in between the 3 modules, R modules, then this is called a short exact sequence. So first one is f0 and this is f3. So what is f3? F3 is just f3 of x is 0 for all x belongs to f3. And what is f0? F0 is obvious. F0 of 0 is 0. There is only one element in domain. So that's why f0 and f3 is not written here. It's the only important part is f1 and f2. So this is called short exact sequence. It is called short exact sequence. Obviously, this f1 must be injective and f2 must be surjective, because kernel of f3 is whole m3. So kernel of f3 is m3. So that must be equal to the image of f2. So that means f2 is onto map and f1 is injective, because kernel of f1 is just image of m1, and if image of f0 is 0. Image of f0 is nothing, it's just 0. Set country only 0 element. So that means if it is a short exact sequence, then f1 is injective and f2 is surjective. And obviously f2 compose f1 is 0. That is also important. So this is called short exact sequence. One example is say 0 to 2z inclusion map. I then inclusion 2z to z, there is the inclusion map. All even number goes to the even number. Identity I of this I is the inclusion map. I of 2x equal to 2x for all x integer. And this is a projection map. You know that what is the projection map? Z to z0, z to z2. This all even element pi of any odd element, it goes to 1 bar, and pi of all even element goes to 0 bar. So there is only 2 elements in Z2, 0 bar and 1 bar. And this is a short exact sequence. This pi is a projection map onto projection map, and I is the inclusion map. So this is an important example of short exact sequence. Now, when a sequence is called split exact sequence of module. So exact sequence, this is an exact sequence, 0 to m1 is short exact sequence, m dash to f, then m to g, m double dash, and then goes to g, 0. So g is surjective and f is injective, and g compose f is 0. And this is a exact sequence of R module, and then it is called split if there is an R homomorphism from M double dash to M. So if there is a R homomorphism from here to here, so if there is a sort of it is not inverse, it's like a right inverse actually. G compose T is I. So G compose T is basically on M double dash to M double dash. And this is identity. So G compose T X is X for all X in M double dash. So if there is such a map, then such a R homomorphism T, then it is called split. This is called split sequence, split exact sequence. Now, one important result is this: you start from 0, then I, from I to M to I is the inclusion map. What is the inclusion map? Natural inclusion map. And what is the natural inclusion map? That is from M to M direct sum n. So this is a natural map. So I of x is x comma 0 is the inclusion map. And this is a projection map that x comma y goes to y. That's a pi is a projection map. That's obviously onto, and this is injective inclusion map. Then we have a map from n to this in the opposite direction, the T map. The T map is just T of y is 0 comma y, and then what happened? Then G, what is G of T? So G of Ty is G of 0 compose 0 comma y, and 0 comma y pi of 0 that is sorry, it is not 0, G, it is a pi. Here it's pi. So pi of 0 comma y is just a y, so it is identity in n. So that's why it is a split map. So splitting, that sequence is called split, and that map T is called splitting map. This T is named as splitting map. If such a T exists, then we call that T as a splitting map, and this is a important example of split exact sequence. So the idea is that the third one, that 0 M, and last one is n0, and the middle one is M direction n. So whether it is true for all splitting sequence, this is a result. So yes, it is true. So if this exact sequence 0 M dash M double dash 0 is a split exact sequence, then M is actually isomorphic to M direct sum M double dash. That is very important result. And there is an exists an R isomorph R homomorphism S from M to M dash. Then since it is split, we have a map here T, and not only that, we have a map here also S, so that S compose F. So it's identity on M dash. So two things happen. So not only is back, it's just again one more sort of inverse is actually left inverse, that S compose F is the identity map on M dash. So what is the proof? The proof is, let T, we define T is like that, is a T is the splitting map. We assume that is a splitting sequence. So we assume that is split. So there is a map from which split actually, such that G compose T is actually, this is G compose T. We write GT means it is not G into T, it is G compose T. So this is identity on M double dash. So what happens? Since it is identity, that means T must be injective. So T is injective. Why T is injective? That let Tx equal to 0. That implies that G of T of x equal to, but this is x, so it is x equal to 0. So it is injective. Once Tx equal to 0 implies x equal to 0, that is injective. Therefore, R homomorphism, we know that is to check injectivity, we have to check just for 0 only. Then, so it is injective. Now, what we have to show? Now, take M belongs to x belongs to M. Then what happened? Then x equal to Tgx plus x minus Tg of x. So we decompose x into we have to actually show that any element of M is a can be written as sum of element of M dash and M double dash. So that's we have to prove. Now we write this in the two sum of two elements. So this is T of some gt gx, and gx is actually gx is the element of M double dash. So what is the meaning of that? Means this is belongs to that T M double dash, this part. And what is this? If you take the G of that element, so remember GT is identity, but TG is not identity. Now this is GX, so it is a R homomorphism, so it's a linear. So that is, but GT is identity, so Gx minus Gx, so it is 0. So that means it is equation to the kernel. So this part is actually in the kernel. So this part is actually in the kernel of G. So this is belongs to the kernel of G. So that means any element of M can be written as sum of two elements. One element is belongs to T of M double dash, and another is in kernel of G. Now what happened? Now is there any common element of that? So take Y belongs to that belongs to the intersection of these two, kernel of that. Now since Y belongs to T M double dash, that means Y is actually sort of some T Z. For some Z belongs to M double dash, and is kernel of G also. So that means GY is 0. So that means GT Z is 0. That means Z equal to 0. So GT Z is equal to Z actually. So that means what? Z equal to 0 means Y equal to 0, because Y equal to TZ. So it is 0. So 0 is the only element common in these two. That means what? That means any element of M can be written as sum of two elements of one is T M double dash and another is kernel of G, and so that's a direct sum. So this is actually the direct sum of M double dash, direct sum at kernel of G. But what is kernel of G? We know kernel of G is, since it is exact, so kernel of G is actually image of F. Now F is injective. That means what? That means this is isomorphic to the image of is F is isomorphic to M dash. And T is injective. We have T is injective. Since T is injective, this T of M dash, M double dash is isomorphic to M double dash. Because T and F both are injective. So if it is split, then M is actually the isomorphic to the direction of other two side by side, left and right side module. So and then we also have this element that S, one function from M to M dash S. How do you construct that S? So it is a split. That means M is actually isomorphic to Tm double dash plus this is image of F, means it is direct sum F of M dash. So this is actually equal. These are equal. It's isomorphic to M double dash direct sum M dash, but it's actually M is equal to T M double dash direct sum F M dash. Now you take a that pi 1 is a projection map on M. So you take a projection map of M pi 1. So you take a projection map pi 1 is a projection map of M. onto f m dash. So f m dash is a submodule of M, and you take the projection map. Since it is a isomorphic, that M is actually this. What is this? So M is actually T M double dash direct sum F M dash. So from F M dash. So there is a projection map. So you know that N1 direct sum N2 goes to N2 has a projection map. So 0 comma x comma y goes to y. So you take that projection map pi 1 and take S as a map F inverse pi 1. F inverse pi. So what is this? So we just from M to Fm dash, then take F inverse. So F may not be surjective. So F inverse may not exist, but if you just restrict your map, inverse map onto Fm dash, then it is obviously that this inverse exists. So F inverse F may not be surjective, but F inverse exists on not from M to M dash, it is actually from Fm dash to M dash. Because Fm dash is the whole range, the range of F. So take the inverse of that. That map is, we define that map as our S, and in that case Fs is actually pi 1. That identity map on M dash. So this proved that there is a map S such that from M to M dash such that SF is actually identity on M dash. So actually you have two reverse map. If you have a split exact sequence, then F and G both have a sort of one right inverse and another left inverse. So reverse map, if that sequence is split exact sequence. And then the middle module is actually direction of the other two modules, left and right module. Now there's a dual module. It's like a dual vector space. It's a dual module. So let M and N are R module. The set S is of all R homomorphism, all homomorphism from M to N. So it is a collection of all homomorphism from like R linear map in vector space. M to N has a natural R module structure. So that set of all R homomorphism is again a module, R module. Why? So we have to define some addition and scalar multiplication on that set. So take two element F and G from S. So you take two element, we have to define F plus G. What is F plus G? F plus G of X is just Fx plus Gx. X belongs to M, because F and G both F and G both are function from M to N. Now, how do you define A into F? A into F is naturally you define A into F of X is A into Fx, and A is from R. So it is scalar multiplier. So we define that. Now this forms a module. So this addition and scalar multiplication forms this S as a module, R module. Now this module is called home of Mn with respect to R. That module is called homomorphism module. Home M to N. So set up all R homomorphism from M to N, like a vector space, like a dual space. Now if N equal to R, that home from M to R, that is called a dual module. If especially is actually set of all such F from M to R. It is like in a field from V to F, that F is a field, then V to F is a set of all such linear map from V to F is actually called that dual space. So here it's a dual module, same thing. It's a generalization of the dual space, and in this called dual module of M. Now, what is the property of this? One thing is, if any R module M is any R module, and there is an exact sequence. This is the exact sequence: 0, N dash, N double dash 0. That means F is injective, G is surjective, and G compose F compose G is null. Sorry, G compose F is null. Then this induced an exact sequence on the homomorphism. So n dash has a homomorphism m home from m to m dash, and n has a homomorphism r home set of all r homomorphism is called home of mn, and then you can write r here, and from n double dash we can construct the home of m to m double dash, and this is a exact sequence. How can construct this exact sequence? So we have to define two functions then, f star and g star from f and g, such that f star is injective and g star is surjective, and g star compose f star is zero map. So how do you define f star? F star is actually function from home m n dash to home m n dash. So what is the meaning of that? So you have to take so there is a function from this. So there is a map, say alpha. So alpha is a R linear map from m to m dash. That means alpha is home m dash. Now we have to define a map from m to n. M to n. That will be in the home of m to n. So what will be the then f star f? F star f is just, what is f? F is here m dash to n. So we define f star alpha as f compose alpha. So f compose alpha is actually this map, this composition map from m to n. So since alpha is r homomorphism from m to m dash, and f is r homomorphism from n dash to m, that's f alpha is r homomorphism from m to m dash m to n. So we define f star alpha as f compose alpha. So that therefore that f star, that map f star whose input is a r homomorphism, given output f alpha is another homomorphism, r homomorphism. So it is from alpha goes to f alpha. F is not a f into alpha, it is f compose alpha. That f star map. So input of f star is a r homomorphism, and output is also an r homomorphism from m to n, and input is from m to m dash. So we define like that. So similarly we define g. Similarly we can define g. Is again g is clear. So we have a map from g from n to n double dash. There is a map g. Now you have to take an element from m to n. So this, take an element from say beta, and you define that g star beta is the g compose beta. G compose beta is the g star beta, and that g star beta is now from m to m double dash. So it is a home of it belongs to the home set of all homomorphisms of m to n double dash. Now we have to show this forms an exact sequence. That's why I just omit that proof. I omit here, and you can check. You can check that this we define f star and g star. We define now that f star and g star gives that sequence as exact sequence. So you have to prove three things: that you have to show that f star is injective, g star is surjective, and g star compose f star is a null homomorphism. So that we have to show, and that is easy to check. So we omit here. Now, one thing is important is this. It's called 4 lemma and 5 lemma. So what is 4 lemma? So say this is the exact sequence, exact rows. That means there is a B, C, D, R module with that sequence is exact. So this sequence is exact. So there is some function. No need of writing that function. Some function is there, and that are exact sequence. And there is a map from A to A dash. There is a map, say alpha. There is a map from B to B dash. It's called beta. There is a map from C to C dash. It's called gamma. And there is a map from D to D dash. It's called delta. And there is some other map here: A to B, B to C, C to D, A dash to B dash, B dash to C dash, and C dash to D dash. That ABC is the exact sequence, and A dash, B dash, C dash is also an exact sequence. So exact rows means that two rows are exact sequence. Now, what is the theorem lemma? The lemma is there is a 4 things, so that's called 4 lemma. If beta and delta are injective, that beta and delta are injective, and alpha is surjective, that alpha is surjective and this beta and delta is injective, then the gamma is injective. Gamma must be injective. Again, we just omit that proof. Just checking some manipulation that you have to check taking elements. So we omit that proof. So similar fold lemma is there. Suppose one has the following commutative diagram. Oh, by the way, that is a commutative. That diagram commutative means, what is the meaning of the diagram commutative? So the meaning is this: if there is a map F and if there is a map F dash, the diagram commutative means that this beta compose F is actually F dash compose alpha. That is called diagram commute. So whatever, if you start take X here and if you go you get Fx here and take beta of Fx in beta dash b dash. Now someone can take alpha x, so alpha x in a dash, and then f dash alpha x is in b dash, and that two must be equal. That is called diagram commutes. And here also same thing, like if it is g dash h dash, and then also that the gamma compose g is g dash compose beta and delta compose h is h dash compose gamma. That is called diagram commutes. Again, that's a similar type of thing. Is the two rows are exact, and again there is a beta function. Other some f y f g is there above. So these are exact. B C D is exact. B dash C dash D dash is exact sequence. Beta, gamma, delta, and say eta from E to E dash. Then again the diagram commutes, and if beta and delta is surjective now. Here alpha is surjective, beta and delta is injective. Now beta is delta is surjective, eta is injective, then gamma is surjective. So again, we just omit that proof. It is just laborious checking. You can check or you can omit the proof. The five lemma is actually the extension of the four lemma. So if there are five in a row, and this each row is exact, and this function are delta eta. Then using fold lemma, you can prove that if beta and delta is isomorphism, alpha is surjective and eta is injective. Now you use the fold lemma for ABCD and fold lemma for BCDE, what you will get? Now alpha is surjective, beta and delta is isomorphic, that means injective, that means gamma is injective. Now in the side by side BCD, for BCD, your beta and delta is isomorphism, that means this is surjective, and eta is injective, that means gamma is surjective. So gamma is injective as well as surjective from the previous two lemma, fold lemma. First fold lemma used on ABC, D, A dash, B dash, C dash, D dash, sorry, this is D dash. And then we use the fold lemma, or the second part of the fold lemma, B, C, D, E, and B dash, C dash, D dash, E dash. We prove gamma is surjective as well as injective, so gamma is isomorphism. So if beta and delta is isomorphism, and your alpha is surjective and eta is injective, and the two rows are exact, and this diagram commutes. By the way, the diagram must commute. Then gamma is an isomorphism. That is an important lemma. It's called five lemma. So this is the end of this lecture. And this is the end of this course also.